close your eyes for a moment. I want you to do something that sounds incredibly simple, but is actually one of the most impossible tasks your brain has ever been asked to perform. I want you to imagine nothing. Not darkness, not emptiness, not a black void stretching out in every direction. I mean absolutely nothing. No space, no time, no darkness because darkness is something. No emptiness because emptiness implies a container that is empty, and a container is something. No dimensions, no directions, no up, no down, no left, no right, no here, no there, no now, no then. I want you to imagine the complete and total absence of everything that has ever existed, could ever exist, or will ever exist. Can you do it? I already know the answer. You cannot. Your brain, physically, neurologically, fundamentally, cannot process the concept of true nothing because your brain evolved to navigate a world of things. Your neurons fire in patterns that represent objects, spaces, relationships between things. Even when you think you are imagining nothing, you are imagining a dark, empty space, and that dark, empty space is something. That darkness has a color. That emptiness has a dimension. That void has a location in your mind's eye. You have failed the task before you even began, and that is not an insult. It is one of the most profound revelations about the nature of human consciousness and the limits of human cognition. Every human being who has ever lived has failed this task. Every genius, every philosopher, every physicist, every mystic, every child who ever stared up at the stars and wondered where everything came from. None of them could imagine true nothing. And yet here is the question that has haunted humanity for as long as we have been capable of asking questions. Before the Big Bang, before the universe existed, before space and time, and matter and energy and light and darkness, what was there? Was there nothing? And if there was nothing, how could nothing exist? How could nothing be a state of affairs? How could nothing give rise to everything? How could the absence of all things produce all things? This is not just a question, this is the question. This is the deepest, most fundamental, most mind-bending question that any conscious being in this universe can ask. And today, right now, in this video, we are going to go deeper into this question than you have ever gone before. We are going to journey to the very edge of human knowledge, to the place where physics breaks down, where mathematics becomes poetry, where science meets philosophy, where the known meets the unknown, and where the greatest minds in human history have stood in awe and admitted that they do not know the answer. But before we begin this journey, let me tell you what we are going to cover, because the depth of what we are about to explore is unlike anything you have experienced in a single video. We are going to start by dismantling everything you think you know about the word nothing. We are going to discover that nothing is not simple. Nothing is not obvious. Nothing is, in fact, one of the most complex, debated, paradoxical, and fascinating concepts in all of human thought. Philosophers have argued about nothing for over 2,500 years. Physicists have discovered that what we call empty space is actually a seething, bubbling, frothing ocean of activity. Quantum mechanics has revealed that nothing is unstable, that nothing cannot remain nothing, that the vacuum of space is pregnant with potential, buzzing with virtual particles that pop into existence and vanish again in timescales so short that your mind cannot comprehend them. We are going to walk through the Big Bang itself, not the cartoon version you have seen in documentaries, but the real, detailed, step-by-step unfolding of the first moments of our universe, from the Planck epoch at 10 to the power of -43 seconds, all the way through inflation, nucleosynthesis, and the formation of the first atoms. We are going to explore 7 major scientific theories about what existed before the Big Bang, including Stephen Hawking's no-boundary proposal, Alexander Vilenkin's theory that the universe quantum tunneled out of literal nothing, the eternal inflation model and the multiverse, Roger Penrose's conformal cyclic cosmology, string theory and the ekpyrotic model, loop quantum cosmology and the Big Bounce, and information theoretic approaches, including the mathematical universe hypothesis. We are going to hear what Albert Einstein, Stephen Hawking, Roger Penrose, Lawrence Krauss, Alexander Vilenkin, Sean Carroll, and other brilliant minds have said about this question. We are going to confront the deepest unsolved mysteries in physics, including the cosmological constant problem, the arrow of time, the fine-tuning problem, and the question of where the laws of physics themselves came from. We are going to examine the intersection of science, philosophy, and theology, not to advocate for any particular worldview, but to honestly and deeply explore how different frameworks of human thought approach this ultimate question. And we are going to look at the cutting edge of modern research, from the James Webb Space Telescope to gravitational wave detectors to the search for quantum gravity, to understand what humanity might discover in the coming decades. This is going to be a journey, a long, deep, meditative, mind-expanding journey. And I promise you this: by the end of this video, you will not see the universe the same way you did when you started. You will not see nothing the same way. You will not see yourself the same way. Because to ask what came before the Big Bang is to ask the most fundamental question about existence itself. And the answer, or the mystery of the answer, changes everything. Now, before we dive in, I have a request. I want you to pause for just a moment and ask yourself this question. What do you think existed before the Big Bang? Do not overthink it. Just go with your gut. Do you think there was nothing? Do you think there was something? Do you think the question even makes sense? Whatever your answer is, hold on to it. Write it down in the comments right now. Write the word nothing or something or I do not know. Because by the end of this video, I want to come back to this moment and see if your answer has changed. And I genuinely believe that for many of you, it will. This is the kind of video that changes minds, not through persuasion or argument, but through the sheer power of what we know, what we do not know, and what we are still discovering. If you are the kind of person who lies awake at night thinking about these questions, if you are the kind of person who looks up at the stars and feels simultaneously tiny and infinite, if you are the kind of person who believes that understanding the universe is one of the most beautiful things a human being can do, then this channel is for you. Hit that subscribe button because we go deep here. We go deeper than anyone else, and this is just the beginning. Let us start with the most deceptive word in the human language. Nothing. Think about how casually we use this word. What are you doing? Nothing. What is in the box? Nothing. What happened? Nothing. In everyday language, nothing is simple. It means the absence of something specific, the absence of activity, the absence of contents, the absence of events. But this everyday meaning is a shadow, a pale reflection, a toy version of what nothing truly means when we push the concept to its absolute limit. When we ask what existed before the Big Bang, we are not asking what was in the box. We are asking about the total, complete, absolute absence of everything, including the box itself, including the space the box would occupy, including the time during which the box would exist, including the very concept of boxes, and space and time, and existence and concepts. We are asking about a level of nothing that is so extreme, so radical, so total, that our language literally does not have the tools to describe it. The ancient Greek philosophers were the first to wrestle seriously with this problem, and they immediately realized how deeply troubling it is. Around 500 years before the Common Era, a philosopher named Parmenides made an argument that still echoes through the halls of philosophy today. Parmenides said that nothing cannot exist. His reasoning was deceptively simple and profoundly powerful. To think about nothing, you must think about something. The very act of contemplating nothing turns it into an object of thought, which means it is something. You cannot point to nothing because there is no nothing to point to. You cannot describe nothing because description requires a subject, and nothing is not a subject. Nothing, Parmenides argued, is a logical impossibility. It is a word that refers to its own absence. It is a concept that negates itself the moment you conceive it. Existence is all there is. There has always been something, and there will always be something, because nothing is impossible. This was radical, this was mind-bending. And in many ways, modern physics has circled all the way back to a version of this ancient insight, as we will see. But not everyone agreed with Parmenides. Another school of Greek thought, the atomists led by Leucippus and his student Democritus, argued that nothing most certainly does exist. They called it the void. The void was the empty space through which atoms moved. Without the void, atoms could not move, and without movement, nothing could happen. The void was real, it was necessary, and it was nothing. Empty space, the absence of matter. A stage upon which the drama of existence played out. This was a fundamentally different conception of nothing. For the atomists, nothing was not the absence of everything. It was the absence of matter within a framework of space. Space itself was something, but the emptiness within space was nothing. It was a more modest, more practical definition, and it worked beautifully for thinking about the physical world. Then came Aristotle, one of the most influential thinkers in human history, and he rejected the void entirely. Aristotle famously declared that nature abhors a vacuum. He argued that true emptiness is impossible because the surrounding matter would always rush in to fill any gap. If you tried to create a void, air would rush in. If you removed the air, the walls of the container would collapse inward. Every attempt to create nothing would be defeated by something. For nearly 2,000 years, Aristotle's view dominated Western thought. The idea that true emptiness could exist was considered absurd, impossible, even heretical. It was not until the scientific revolution of the 16th and 17th centuries that this view was seriously challenged. And when it was challenged, the results were shocking. In 1643, an Italian physicist named Evangelista Torricelli performed a beautiful experiment. He took a glass tube sealed at one end, filled it with mercury, and inverted it into a dish of mercury. The mercury in the tube dropped to a certain level, and above it, at the sealed end of the tube, there was... What was in that space above the mercury? There was no air, there was no mercury, there was apparently nothing. Torricelli had created the first artificial vacuum, or had he? This question ignited a fierce debate. Was the space above the mercury truly empty, or was it filled with some invisible substance? The debate raged for decades. Blaise Pascal performed further experiments, carrying mercury barometers up mountains to show that the mercury level changed with altitude, proving that it was atmospheric pressure pushing the mercury up, and that the space above was indeed a vacuum. But even Pascal was not entirely sure what nothing meant in this context. And he was right to be uncertain, because as we now know, even the most perfect vacuum we can create is far from empty. It is full of quantum fields, virtual particles, and zero-point energy. But we are getting ahead of ourselves. We need to take this step by step. The philosopher who posed the question most sharply, more sharply than anyone before or since, was Gottfried Wilhelm Leibniz. In 1714, Leibniz asked a question that has been called the most fundamental question in all of philosophy. He asked, "Why is there something rather than nothing?" Think about that for a moment. Of all the possible states of affairs, the simplest, the most natural, the most expected would seem to be nothing at all. No universe, no matter, no energy, no space, no time, nothing. That seems like the default state. And yet, here we are. There is a universe. There are galaxies and stars and planets and oceans and mountains and trees and people and thoughts and questions. There is an astonishing amount of something. Why? What is the reason for all of this existing instead of nothing existing? Leibniz's answer was God. He argued that there must be a necessary being whose existence explains itself, and that being is the reason why there is something rather than nothing. But whether you accept that answer or not, the question itself remains one of the deepest questions ever posed. Because even if you do not believe in God, you still have to explain why there is something. Even if you say the universe just exists as a brute fact, you are still making a claim that requires justification. Why does the universe just exist? Why does it exist rather than not existing? What is it about reality that makes existence the case rather than non-existence? These questions have not been answered. They may never be answered. But they are the questions that drive us to the very edge of what we can know. Now, in modern physics, the concept of nothing has been refined, deepened, complicated, and made far stranger than any ancient philosopher could have imagined. The physicist and author Lawrence Krauss has proposed a useful framework for thinking about the different levels of nothing, and I want to walk through these carefully because they are essential for understanding the rest of this video. The first level of nothing is what we might call empty space. Imagine you could remove every particle of matter, every photon of light, every neutrino, every cosmic ray, every atom, every subatomic particle from a region of space. What would be left? Intuitively, you might say nothing. And in the everyday sense, you would be right. There is nothing there. No objects, no particles, no radiation. Just empty space. But here's the critical point. Space itself is still there. The fabric of space-time, the arena in which things exist, is still present. And as we have learned from Einstein's general theory of relativity, space-time is not nothing. Space-time is a dynamical entity. It can bend, stretch, warp, ripple, and carry energy. It is affected by matter and energy, and it affects them in turn. Gravity is not a force pulling objects together. It is the curvature of space-time caused by the presence of mass and energy. So, even when you remove everything from a region of space, you have not achieved nothing. You have achieved empty space, which is a very different thing. The second level of nothing goes deeper. Imagine you could remove not just all the matter and energy, but space itself. Imagine there is no spatial framework, no arena, no stage, and imagine you also remove time. No before, no after, no duration, no sequence, no space-time at all. What is left? Well, in some formulations of quantum mechanics, what is left are quantum fields. The fundamental quantum fields that permeate reality, the electron field, the photon field, the quark fields, the Higgs field, and all the others, may be more fundamental than space-time itself. Some physicists believe that space-time emerges from these fields rather than the other way around. So, even when you strip away space-time, there might still be an underlying quantum reality. And that quantum reality is not nothing. The third level of nothing is the most extreme. Imagine you remove space-time, quantum fields, the laws of physics, mathematical structures, potentialities, possibilities, probabilities, everything. Not just the things that exist, but the rules that govern existence. Not just the actors on the stage, but the stage, the theater, the city, the country, the planet, the universe, and the very concept of staging a play. This is what philosophers call absolute nothing. It is the most radical form of nothing conceivable. It is the nothing that Parmenides said was impossible. It is the nothing that makes your brain hurt when you try to think about it, because there are literally no mental tools that can represent it. And this is where the debate gets really interesting. Because when physicists say the universe came from nothing, which nothing do they mean? When Lawrence Krauss says a universe from nothing, he means the first level, maybe the second level. Empty space or the quantum vacuum, spontaneously producing a universe. But his critics, particularly the philosopher David Albert, have pointed out that this is not really nothing. The quantum vacuum is something. It has structure, it obeys laws, it has properties. Calling it nothing is, Albert argued, a bait and switch. True nothing, the philosophical nothing, the third level, is far more radical than anything Krauss describes. And so the question remains, did the universe come from true nothing? Can anything come from true nothing? Is true nothing even possible? These are the questions we are going to wrestle with. And I will tell you right now, there are no easy answers, but there are extraordinary, beautiful, terrifying, wonderful possibilities. There is another aspect of nothing that we need to discuss before we move on, and it is perhaps the most counterintuitive aspect of all. Nothing might be unstable. Let me explain what I mean. In our everyday experience, nothing seems like the most stable state possible. If there is nothing, then nothing can change, because there is nothing to do the changing. Nothing should remain nothing forever. But physics tells a very different story. In quantum mechanics, there is a principle called the Heisenberg uncertainty principle. You have probably heard of it. It says that certain pairs of physical quantities cannot both be precisely determined at the same time. The most famous pairs, position and momentum. You cannot know both where a particle is and how fast it is moving with perfect precision. The more precisely you know one, the less precisely you know the other. This is not a limitation of our instruments. It is a fundamental feature of reality. Nature itself does not have precise values for both quantities simultaneously. But there is another pair of quantities governed by the uncertainty principle that is even more relevant to our discussion, energy and time. The uncertainty principle for energy and time says that over a sufficiently short period of time, the energy of a system can fluctuate by a significant amount. The shorter the time interval, the larger the possible energy fluctuation. This means that even in a perfect vacuum, even in what we call empty space, energy fluctuations are constantly occurring. Tiny amounts of energy are spontaneously appearing and disappearing on incredibly short timescales. These energy fluctuations manifest as virtual particles, pairs of particles and antiparticles that briefly pop into existence, fly apart, come back together, and annihilate each other, returning their borrowed energy to the vacuum. This happens everywhere, all the time. The vacuum of space is not empty. It is a roiling, seething, frothing ocean of virtual particles appearing and vanishing, billions of times per second, in every cubic centimeter of space. And this is not theoretical speculation. This has been experimentally confirmed in multiple ways. The most famous experimental confirmation is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948, and confirmed experimentally by Steve Lamoureux in 1997. The setup is beautifully simple. Take two flat, parallel metal plates and place them very close together in a vacuum. According to classical physics, nothing should happen. The plates are an empty space. There is nothing between them or around them. But according to quantum mechanics, the virtual particles in the vacuum create a real, measurable force between the plates. Here is why. Virtual particles come in all wavelengths. Between the plates, only wavelengths that fit neatly between the plates can exist, like standing waves on a guitar string. Outside the plates, all wavelengths are possible. This means there are more virtual particles pushing on the plates from the outside than from the inside. The result is a net force pushing the plates together. This force is tiny, but it is real, and it has been measured with extraordinary precision. The Casimir effect proves, experimentally, that the vacuum is not empty. Nothing is something. The emptiest emptiness we can create is still full of quantum activity. This is not a metaphor. This is not a philosophical interpretation. This is a measured, confirmed, quantified physical fact. The vacuum has energy. The vacuum has structure. The vacuum does things. And this has the most extraordinary implications for the question of what existed before the Big Bang. If the vacuum is not truly nothing, if even the most perfect emptiness is full of quantum fluctuations and virtual particles, then what does this mean for the origin of the universe? Here is one possibility that many physicists take seriously. Perhaps the entire universe is a quantum fluctuation. Perhaps our universe, with all its galaxies and stars, and planets and people, is a virtual particle that appeared from the quantum vacuum and simply has not annihilated yet. This sounds insane. This sounds like science fiction, but it is a serious scientific hypothesis, and the mathematics behind it is well developed. In 1973, the physicist Edward Tryon published a paper in the journal Nature with the title, "Is the Universe a Vacuum Fluctuation?" Tryon's key insight was this: the total energy of the universe might be exactly zero. The positive energy of all the matter and radiation in the universe might be precisely balanced by the negative gravitational energy of all that matter and radiation attracting each other. If the total energy is zero, then the universe could have appeared from nothing without violating conservation of energy. No energy was created. The positive and negative energies appeared simultaneously and balance each other perfectly. The universe is, in a sense, an elaborate way of arranging zero. It is nothing, just rearranged. Tryon himself was modest about his proposal. He wrote, "I offer the modest proposal that our universe is simply one of those things which happen from time to time. This is a staggering idea. The universe is just one of those things that happens from time to time. Like a virtual particle pair in the vacuum. It popped into existence, and it just happens to be a very, very long-lived fluctuation. Long-lived enough for galaxies to form, for stars to ignite, for planets to coalesce, for life to evolve, for consciousness to emerge, for you and me to sit here and wonder where it all came from. And the answer, according to Tryon, might be from nothing. From a quantum fluctuation in the void. Just one of those things that happen from time to time." Now, Tryon's original proposal had some problems. Most importantly, quantum fluctuations that borrow large amounts of energy can only exist for very short times. The universe has existed for 13.8 billion years, which is a very long time for a quantum fluctuation. But this problem was solved by the concept of cosmic inflation, which we will discuss in great detail shortly. Inflation provides a mechanism by which a tiny quantum fluctuation can be rapidly expanded to cosmic scales, and once inflation begins, the borrowed energy is essentially paid back by the negative gravitational energy of the inflating space. The fluctuation does not need to disappear. It can grow, expand, cool, and evolve into a universe. Into our universe. But I want to pause here and acknowledge the elephant in the room. All of this talk about quantum fluctuations and the quantum vacuum assumes that quantum mechanics exists. It assumes that there are laws of physics, that there are quantum fields, that there is a framework within which fluctuations can occur. And that framework is not nothing. The quantum vacuum is a state within a theory. It is the lowest energy state of a system governed by quantum field theory. But the theory itself, the mathematical framework, the laws that determine what the vacuum can and cannot do, those are something. They are not physical objects, but they are real in the sense that they determine what happens. And so the question pushes deeper. Where did the laws of physics come from? If the universe is a quantum fluctuation, what determined the rules governing that fluctuation? Why quantum mechanics and not something else? Why these specific laws and not different ones? This is the problem of the meta-laws, and it is one of the deepest unsolved problems in all of science and philosophy. Some physicists try to dodge this problem by arguing that the laws of physics are not external to the universe. They do not exist somewhere else, governing the universe from outside. Instead, the laws and the universe are the same thing. The laws are descriptions of what the universe does, not prescriptions imposed from above. In this view, asking where the laws came from is like asking where the rules of chess exist when no one is playing chess. The rules do not exist independently. They only exist as descriptions of the game, and the game is the universe. But this answer, while clever, does not fully satisfy. Because even if the laws are descriptions rather than prescriptions, the fact that the universe behaves in a law-like manner at all is something that requires explanation. Why does the universe follow patterns? Why is it comprehensible? Why does mathematics, a product of human thought, describe the universe with such breathtaking accuracy? Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences, and it remains one of the deepest mysteries we know of. Let us now turn to the Big Bang itself, because before we can understand what came before it, we need to understand what it actually was. And I guarantee you that what you think you know about the Big Bang is probably wrong, or at least incomplete. Let me start by clearing up the most common misconception. The Big Bang was not an explosion. When you hear the words Big Bang, you probably picture a bomb going off in space, an explosion radiating outward from a central point into the surrounding emptiness. This is completely wrong. The Big Bang was not an explosion in space. It was an expansion of space. There was no surrounding emptiness for anything to explode into. There was no central point from which the explosion originated. Space itself was expanding, and it was expanding everywhere simultaneously. Imagine you draw dots on a balloon and then inflate the balloon. As the balloon expands, every dot moves away from every other dot. But no dot is at the center of the expansion. The expansion is happening everywhere on the surface of the balloon equally. Now, this analogy is imperfect because the surface of a balloon is two-dimensional and curved in a way that our three-dimensional universe may not be. But the key insight is correct. The expansion of the universe is not something happening in space. It is something happening to space. Space itself is getting bigger. And in the very early universe, space was expanding at a rate that is almost impossible to comprehend. Here is the timeline of what actually happened, as best as modern physics can reconstruct it. And I want to take this slowly and carefully, because the details matter and they are extraordinary. The very first era of the universe is called the Planck epoch. This covers the time from 0 to approximately 10 to the power of negative 43 seconds after the Big Bang. That number is so small that it is essentially meaningless to the human mind. It is a decimal point, followed by 42 zeros, and then a 1. It is a millionth of a billionth 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 of a second. During this unfathomably tiny sliver of time, the entire universe was smaller than the Planck length, which is approximately 1.6 times 10 to the power of negative 35 meters. This is the smallest meaningful length in physics. Below this scale, our understanding of space and time breaks down completely. The temperature during the Planck epoch was approximately 10 to the power of 32 Kelvin, which is so hot that it makes the center of the hottest star look like absolute zero by comparison. At this temperature and density, all four fundamental forces of nature, gravity, the strong nuclear force, the weak nuclear force, and electromagnetism, were unified into a single force. There was no distinction between them. They were all aspects of one underlying interaction. And here is the critical point. We have no theory that can describe what was happening during the Planck epoch. Our two great theories of physics, general relativity and quantum mechanics, each work brilliantly in their own domain. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles at the smallest scales. But during the Planck epoch, both domains overlap. The universe was so small that quantum effects were dominant, but it was also so dense that gravitational effects were dominant. We need a theory that combines both, a theory of quantum gravity, and we do not have one yet. General relativity breaks down at the Planck scale. It predicts infinities, singularities, nonsensical answers. Quantum mechanics, as currently formulated, does not include gravity. The two theories are fundamentally incompatible, and the Planck epoch is the regime where this incompatibility matters most. This means that the very beginning of the universe, the moment of creation itself, is hidden behind a curtain of ignorance. We cannot calculate what happened. We cannot predict what happened. We can only speculate, guided by fragments of theory and mathematical intuition. The Planck epoch is the ultimate frontier. It is the dragon at the edge of the map. Here be monsters. And yet, physicists are not deterred. They are working to develop theories of quantum gravity, and we will discuss their progress later. But for now, it is important to understand that the very first moment of the universe is, in a very real sense, unknown. After the Planck epoch, things get a little clearer, though only a little. At approximately 10 to the power of negative 43 seconds, the first thing that happened was the separation of gravity from the other three forces. Gravity became its own distinct force, while the strong nuclear force, the weak nuclear force, and electromagnetism remained unified in what is called the grand unified force. This era is called the grand unification epoch, and it lasted from approximately 10 to the power of negative 43 seconds to approximately 10 to the power of negative 36 seconds. During this era, the universe was still unimaginably hot and dense, but it was cooling as it expanded. The grand unified force governed all interactions between particles, and exotic particles that we have never observed in any laboratory existed freely. Among these were magnetic monopoles, hypothetical particles that carry a single magnetic charge, and superheavy X and Y bosons that could transform quarks into leptons and vice versa. These particles are predicted by grand unified theories, but have never been detected. Their absence is actually one of the things that cosmic inflation explains, as we will see. At approximately 10 to the power of negative 36 seconds, something extraordinary happened. The strong nuclear force separated from the electro-weak force, and this separation triggered the most violent event in the history of the universe. Cosmic inflation. Inflation is a theory proposed by Alan Guth in 1980, and later refined by Andre Linde, Andreas Albrecht, Paul Steinhardt, and others. The idea is that for an incredibly brief period, the universe underwent a period of exponential expansion so rapid that it defies comprehension. During inflation, the universe expanded by a factor of at least 10 to the power of 26. That means the universe became at least 100 trillion times larger in a time interval of approximately 10 to the power of negative 32 seconds. To put this in perspective, imagine a bacterium, a single bacterium, smaller than the width of a human hair. Now imagine that bacterium suddenly expanded to the size of the entire observable universe. That is roughly the scale of inflationary expansion. And it happened in a time so short that light, the fastest thing in the universe, could barely travel across a single proton during that interval. This is not a gentle expansion. This is not a gradual swelling. This is a sudden, violent, mind-shattering explosion of space itself, the universe being stretched by an incomprehensible factor in an incomprehensibly short time. And the engine driving this expansion was a hypothetical field called the inflaton field. The inflaton field is thought to have been in a high-energy state called a false vacuum. A false vacuum is a state that appears stable, but is not truly stable. It is like a ball sitting on top of a hill. The ball appears to be at rest, but a tiny push will send it rolling down. The false vacuum of the inflaton field contained enormous energy, and this energy drove the expansion of space. As long as the inflaton field remained in its false vacuum state, the expansion continued exponentially. But eventually, the inflaton field decayed, rolling down from its high-energy state to a low-energy state, and the energy stored in the field was released as a flood of particles and radiation. This event is called reheating, and it is essentially the moment that the Big Bang, as we traditionally think of it, actually began. The particles created during reheating were the raw material from which everything in the universe would eventually be built. Every star, every galaxy, every planet, every organism, every atom in your body can trace its origin back to this moment of reheating, when the energy of the inflaton field was converted into the matter and radiation of the newborn universe. Inflation solves several major problems in cosmology. The first is the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire sky, we find that it is remarkably uniform. The temperature is the same in every direction to 1 part in 100,000. But here is the problem. Regions on opposite sides of the sky have never been in contact with each other. Light has not had time to travel from one side to the other in the 13.8 billion years since the Big Bang. So, how can they have the same temperature? In everyday life, things reach the same temperature through contact. You put a hot cup of coffee on a cold table, and they exchange heat until they reach the same temperature. But regions of the universe that have never been in contact cannot exchange heat. They should have different temperatures, and yet they do not. Inflation solves this problem beautifully. Before inflation, the entire observable universe was contained in a region so small that every part of it was in intimate contact with every other part. Heat flowed freely. Temperatures equalized. And then inflation stretched this tiny, uniform region to cosmic scales. The uniformity we see today is a relic of this pre-inflationary contact. The second problem inflation solves is the flatness problem. The geometry of the universe is remarkably close to flat, meaning that the angles of a triangle add up to 180 degrees, parallel lines remain parallel, and the usual rules of Euclidean geometry apply on cosmic scales. But this is extraordinary because the equations of general relativity predict that any slight deviation from perfect flatness should grow over time. If the universe were even slightly positively curved at the beginning, it should have collapsed back on itself long ago. If it were even slightly negatively curved, it should have expanded so fast that no structures could ever form. The fact that the universe is flat, or very nearly flat, after 13.8 billion years of evolution, means that at the very beginning, the flatness had to be fine-tuned to an almost impossible degree. The initial curvature had to be exactly right to 1 part in 10 to the power of 60. Inflation explains this because exponential expansion flattens any curvature, just as inflating a balloon makes its surface appear flatter and flatter. No matter what the initial curvature was, inflation stretched the universe so dramatically that it appears perfectly flat today. The third problem inflation solves is the monopole problem. Grand unified theories predict that magnetic monopoles should have been produced in enormous quantities in the early universe. But we have never observed a single magnetic monopole. Inflation explains this by diluting the monopole density so dramatically that there might be fewer than one monopole in the entire observable universe. Inflation swept them away, scattered them across an unimaginably vast cosmos, leaving our little patch of the universe monopole-free. But here is what is truly mind-blowing about inflation, and this connects directly to our central question. The quantum fluctuations that occurred during inflation are responsible for everything we see today. During inflation, the universe was dominated by the inflaton field, and like all quantum fields, the inflaton field experienced quantum fluctuations, tiny random variations in the energy density of the field. Under normal circumstances, these fluctuations would be unimaginably small and would quickly average out. But inflation stretched them. It took fluctuations that were smaller than a proton and expanded them to astronomical scales. These fluctuations became variations in the density of the universe, regions that were slightly denser and regions that were slightly less dense. And these density variations were the seeds of all cosmic structure. The slightly denser regions had slightly stronger gravity, which attracted more matter, making them denser still. Over millions and billions of years, these tiny quantum fluctuations grew into galaxies, clusters of galaxies, superclusters, filaments, and the vast cosmic web that spans the observable universe. Think about what this means. The largest structures in the universe, structures spanning hundreds of millions of light years, structures containing billions of galaxies, each containing hundreds of billions of stars, were determined by quantum fluctuations during the first fraction of a second of the universe's existence. The position of our galaxy, the location of our solar system, the existence of our planet, and ultimately the existence of you and me, are all consequences of quantum randomness amplified by inflation. If the quantum fluctuations had been slightly different, the galaxies would be in different places. Our solar system might not exist, you might not exist. The specific arrangement of matter in our universe, every star, every planet, every mountain, every ocean, every person, is a frozen image of the quantum fluctuations that occurred during the first 10 to the power of negative 32 seconds of the universe's existence. This is one of the most extraordinary facts about reality that I know. Your existence is a consequence of a quantum random event that happened 13.8 billion years ago and lasted less than a billionth of a billionth of a billionth of a second. Nothing about your existence was inevitable. Everything about your existence is the result of cosmic chance, amplified by the relentless laws of physics over billions of years, and it all started from something that might have emerged from nothing. After inflation ended and reheating occurred, the universe entered a more familiar phase of its evolution, though still unimaginably extreme by human standards. The universe was a dense, hot plasma of fundamental particles. Quarks and gluons formed a quark-gluon plasma, a state of matter that we have briefly recreated in particle accelerators like the Large Hadron Collider. This phase, the quark epoch, lasted until about 10 to the power of negative 6 seconds, or 1 microsecond after the Big Bang. As the universe continued to cool, the quarks combined to form protons and neutrons. This is the Hadron epoch, lasting from about 1 microsecond to about 1 second after the Big Bang. During this epoch, protons and neutrons and their antiparticles were being created and destroyed in a constant dance of matter and antimatter. And here we encounter one of the most important and poorly understood events in the history of the universe: the asymmetry between matter and antimatter. According to our best understanding of particle physics, the Big Bang should have created exactly equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, converting all their mass into energy, into photons of light. So, if equal amounts of matter and antimatter were created, they should have completely annihilated each other, leaving a universe of pure radiation with no matter at all. No atoms, no molecules, no stars, no planets, no life, no you, no me. Just light. But that is not what happened. For reasons that we still do not fully understand, there was a tiny asymmetry. For every billion antimatter particles, there were 1,000,000,001 matter particles. One extra matter particle for every billion. When the matter and antimatter annihilated, that one extra particle in every billion survived. And those surviving particles, that tiny residue, that minuscule excess, is everything. Every atom in your body, every star in the sky, every galaxy in the cosmos. All of it is that 1 in a billion leftover. We are the rounding error of the universe. We are the crumbs left over from the annihilation. And the fact that this asymmetry existed, that there was one extra particle for every billion, is one of the great unexplained mysteries of physics. We know the asymmetry exists because we exist, but we do not know why it exists. The standard model of particle physics cannot fully explain it. There are theories involving something called CP violation and the Sakharov conditions, but none of them fully account for the observed asymmetry. Why the universe preferred matter over antimatter, even by this tiny amount, remains one of the biggest unsolved questions in all of science, and it is directly related to our central question. Because if the universe came from nothing, or from a symmetric quantum state, why did this asymmetry arise? Why was the universe not perfectly symmetric? Why was there that one extra particle? This tiny imperfection, this minuscule deviation from perfect balance, is the reason anything exists at all. By about 1 second after the Big Bang, the universe had cooled enough for neutrinos to stop interacting with other matter. This event is called neutrino decoupling, and the neutrinos released at this moment are still streaming through the universe today, forming the cosmic neutrino background. We have not yet directly detected this background, but we are working on it. If we ever do detect it, it will give us a window into the universe, as it was just 1 second after the Big Bang, even earlier than the cosmic microwave background. Between about 1 second and about 20 minutes after the Big Bang, the universe was a giant nuclear reactor. This period is called Big Bang nucleosynthesis, and it is one of the most precisely understood periods of the early universe. During this time, protons and neutrons fused together to form the lightest atomic nuclei. Hydrogen nuclei, which are just individual protons, formed naturally. 2 protons and 2 neutrons fused to form helium-4 nuclei. Small amounts of deuterium, helium-3, and lithium-7 were also formed. And that is it. That is all the Big Bang made, just the lightest elements. No carbon, no oxygen, no iron, no gold, nothing heavier than lithium. The heavier elements would have to wait for stars to form, live, and die, fusing heavier elements in their cores and then scattering them across space in spectacular supernova explosions. But the ratio of hydrogen to helium to lithium produced during Big Bang nucleosynthesis is a precise prediction of the Big Bang theory, and it matches observations perfectly. About 75% hydrogen, about 25% helium, and trace amounts of lithium and deuterium. This agreement between prediction and observation is one of the strongest pieces of evidence for the Big Bang theory. After nucleosynthesis, the universe continued to cool and expand, but it was still incredibly hot and dense. For the next 380,000 years, the universe was a plasma, a hot soup of nuclei and free electrons. Photons, particles of light, were constantly being absorbed and re-emitted by the free electrons. Light could not travel in a straight line. The universe was opaque, like being inside a fog. But at about 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin, cool enough for electrons to combine with nuclei to form neutral atoms for the first time. This event is called recombination, and it was one of the most important moments in the history of the universe. Once atoms formed, photons were no longer scattered by free electrons. Light could travel freely through the universe for the first time. The fog cleared. The universe became transparent, and the light released at that moment, the light that was freed when the universe became transparent, is still traveling through the cosmos today. It has been traveling for 13.8 billion years, and it has been stretched by the expansion of the universe from visible light to microwaves. This is the cosmic microwave background radiation, the CMB, and it is one of the most important observations in all of cosmology. The CMB was predicted by George Gamow, Ralph Alpher, and Robert Herman in the late 1940s, and it was accidentally discovered by Arno Penzias and Robert Wilson in 1964. Penzias and Wilson were working at Bell Labs in New Jersey with a large microwave antenna, and they kept picking up a persistent background noise that they could not eliminate. They pointed the antenna in every direction. The noise was the same. They thought it might be pigeon droppings on the antenna. They cleaned the antenna. The noise was still there. They checked every possible source of interference. Nothing explained it. And then they learned that a group of physicists at nearby Princeton University, led by Robert Dicke and Jim Peebles, had predicted that if the Big Bang happened, there should be a faint microwave radiation filling the entire universe, a remnant of the moment when the universe first became transparent. Penzias and Wilson had found it. They had stumbled upon the afterglow of creation. This discovery won them the Nobel Prize in Physics in 1978, and it transformed cosmology from a speculative, philosophical enterprise into a precision science. The CMB is not just proof that the Big Bang happened. It is a snapshot of the universe as it was 380,000 years after the Big Bang. It is the oldest light in the universe, the most distant thing we can see with any form of electromagnetic radiation. And when we map the CMB in exquisite detail, as the COBE, WMAP, and Planck satellites have done, we find something remarkable. It is almost perfectly uniform. The temperature of the CMB is 2.725 Kelvin everywhere in the sky, but it is not exactly uniform. There are tiny fluctuations, variations of about 1 part in 100,000. These tiny temperature variations correspond to tiny density variations in the early universe, regions that were slightly denser and slightly less dense. And these density variations are exactly the quantum fluctuations from the inflationary epoch that I described earlier, stretched to cosmic scales. The pattern of fluctuations in the CMB matches the predictions of inflationary theory with extraordinary precision. This is a stunning confirmation of the idea that quantum fluctuations during the first fraction of a second of the universe's existence seeded all the structure we see today. We can literally see, in the CMB, the quantum origins of the cosmos. We can see the fingerprints of quantum mechanics written across the sky, and from these fingerprints we can work backward to reconstruct the history of the universe to an astonishing level of detail. But the CMB is also a wall. It is the furthest back in time we can see with light. Before recombination, the universe was opaque. No light from that era has survived to the present day. The CMB is like a curtain drawn across the sky, hiding everything that came before 380,000 years after the Big Bang. To see further back, we need other tools. We need gravitational waves, which can pass through the primordial plasma unimpeded. We need neutrinos from the cosmic neutrino background. And we need theoretical physics, the mathematical frameworks that allow us to extrapolate our understanding backward to the very first moments, and perhaps even to the moment before the first moment. This is where we return to our central question. What happened before the Big Bang? What existed before the Big Bang? How could nothing exist before the Big Bang? And now that we understand what the Big Bang actually was, now that we understand the timeline, the physics, the evidence, we are ready to explore the deepest and most mind-bending theories that science has to offer. Before we dive into these theories, I want to take a moment to appreciate where we are in this journey. We have traveled from the everyday meaning of nothing through 2,500 years of philosophical debate. We have discovered that the quantum vacuum is not empty, that virtual particles constantly pop in and out of existence, and that nothing in the quantum sense is already something. We have walked through the Big Bang step by step, from the Planck epoch through inflation, nucleosynthesis, and recombination. We have seen how quantum fluctuations smaller than a proton became the seeds of galaxies. And we have reached the wall, the limit of what light can show us, the boundary beyond which we can only theorize. What comes next is the most speculative, the most debated, the most exciting part of our journey. If you are still here, you are my kind of person. You are someone who is not satisfied with easy answers. You are someone who wants to know the truth, or as close to the truth as we can get, no matter how strange or uncomfortable or mind-bending that truth might be. So, let me ask you to do something. If this video has already taught you something you did not know, or shown you something from a perspective you had not considered, hit the like button right now. It takes 1 second, and it tells the algorithm that this kind of deep, thorough, no shortcuts content is worth sharing with more people. And if you have not subscribed yet, do it now, because what is coming next is even more extraordinary than what you have already heard. Let us begin with one of the most beautiful and elegant ideas in all of theoretical physics, the no-boundary proposal, developed by James Hartley and Stephen Hawking in 1983. To understand this proposal, we first need to understand the problem it was trying to solve. When we apply general relativity to the very early universe and work backward in time, we encounter singularity. A singularity is a point where the equations of general relativity produce infinite values. The density becomes infinite. The curvature of space-time becomes infinite. The temperature becomes infinite. All of physics breaks down. The singularity theorems, proven by Roger Penrose and Stephen Hawking in the late 1960s, showed that under very general conditions, general relativity inevitably predicts singularities. If the universe contains enough matter and energy, and if general relativity is correct, then there must have been a singularity at the beginning of the universe. The Big Bang singularity. This singularity is not just a mathematical nuisance, it is a conceptual catastrophe. A singularity is a place where our theory gives nonsensical answers. It is a place where the theory is telling us that it is wrong, that it is being applied beyond its domain of validity, that something else, something beyond general relativity, must be happening. And this is precisely what Hartley and Hawking set out to address. Their approach was to apply quantum mechanics to the entire universe, not just to particles or fields, but to the universe as a whole. This is quantum cosmology, and it is one of the most ambitious and challenging areas of theoretical physics. In quantum mechanics, A system is described by a wave function, a mathematical object that encodes all the information about the system's possible states. Hartley and Hawking asked, "What is the wave function of the universe? What mathematical object describes the quantum state of the entire cosmos?" To calculate this wave function, they used a technique from quantum field theory called the path integral, developed by Richard Feynman. The basic idea is that to calculate the probability of a quantum system going from one state to another, you sum over all possible paths, all possible histories, that connect the two states. Each path contributes to the sum, and the total gives you the probability. Hartley and Hawking applied this to the universe. They summed over all possible geometries, all possible shapes of space-time, that could describe the history of the universe. But here is the key innovation. When they performed this sum, they used a mathematical trick called Wick rotation, which involves replacing ordinary time with what is called imaginary time. Now, imaginary time sounds like science fiction, but it is a well-established mathematical tool. In mathematics, imaginary numbers are numbers that involve the square root of -1, usually denoted by the letter I. Imaginary time is time measured in imaginary numbers rather than real numbers. This is not as bizarre as it sounds. In special relativity, the space-time interval between two events involves time and space in a specific way, and replacing time with imaginary time turns the space-time interval into a purely spatial quantity. In other words, imaginary time is mathematically equivalent to another dimension of space. And this is the profound insight of the Hartley-Hawking proposal. In imaginary time, the distinction between time and space disappears. Time becomes another dimension of space. And when you have 4 dimensions of space instead of 3 dimensions of space plus 1 dimension of time, something remarkable happens to the singularity. It disappears. In imaginary time, the geometry of the very early universe is smooth and rounded, like the surface of a sphere. There is no singularity, there is no boundary, there is no edge. The universe is finite in extent but has no beginning, just as the surface of the earth is finite in area but has no edge. You can walk forever on the surface of the earth and never reach a boundary. Similarly, in the Hartley-Hawking model, you can trace the history of the universe backward in imaginary time and never reach a beginning. Time does not start at a singularity. It gradually merges with space, becoming more and more space-like as you approach the earliest moments. The Big Bang is not a beginning. It is more like the North Pole of a sphere. It is a point, but it is not a boundary. It is not an edge. It is simply a place where lines of longitude, which we can think of as the histories of particles, converge. Stephen Hawking illustrated this with a beautiful analogy. He said, "Asking what came before the Big Bang is like asking what is north of the North Pole." The question seems meaningful. It uses familiar words. It has the grammatical structure of a legitimate question. But it is, in fact, meaningless. There is nothing north of the North Pole, not because there is some mysterious nothingness up there, but because the concept of north ceases to apply at the North Pole. The North Pole is the northernmost point. Going further north is not impossible. It is incoherent. Similarly, Hawking argued, the Big Bang is the earliest point in time, not because there is some mysterious nothingness before it, but because the concept of before ceases to apply at the Big Bang. The Big Bang is the time equivalent of the North Pole. Going further back is not impossible, it is incoherent. Time does not extend beyond the Big Bang because time, as we understand it, emerges at the Big Bang from a more fundamental geometric structure. This is an extraordinarily elegant idea. It eliminates the singularity. It eliminates the need for initial conditions, because there is no initial boundary. And it provides a mathematical framework for the quantum state of the universe. But it is also deeply controversial. There are several major criticisms. First, the reliance on imaginary time is troubling for many physicists. While imaginary time is a useful mathematical tool, its physical interpretation is unclear. Is imaginary time real? Does the universe actually experience imaginary time? Or is it just a mathematical trick that gives the right answer without corresponding to physical reality? Hawking himself was ambiguous about this. He sometimes suggested that imaginary time is just as real as ordinary time, that the distinction is merely a matter of perspective. But many physicists are uncomfortable with this. They want a theory that describes the universe in terms of real, physical time, not imaginary mathematical time. Second, the no-boundary proposal does not explain why the universe exists. It describes a possible quantum state of the universe, but it does not explain why that quantum state is realized rather than some other state, or rather than no state at all. The universe in Hawking's picture simply is. It has no cause, no creator, no reason. It is a self-contained, self-consistent mathematical structure. Some people find this deeply satisfying. Others find it deeply unsatisfying. It replaces the question, why is there something rather than nothing, with the statement, there just is something, and here's the math. Third, other physicists, particularly Alexander Vilenkin, have argued that the Hartley-Hawking wave function actually describes a universe that is most likely to be empty, which contradicts our observation of a universe full of matter, energy, and structure. This is a technical dispute that involves the detailed mathematics of quantum cosmology, and it has not been fully resolved. And this brings us to our second major theory, which is in many ways the most radical of all. Alexander Vilenkin's proposal that the universe literally, quantum, tunneled out of nothing. Vilenkin, a physicist at Tufts University, published a groundbreaking paper in 1982 titled Creation of Universes from Nothing. In this paper, he proposed that the universe began as a quantum tunneling event from a state of absolute nothingness. To understand quantum tunneling, think about a ball rolling along a flat surface toward a hill. In classical physics, if the ball does not have enough energy to get over the hill, it will roll partway up, slow down, stop, and roll back. It cannot get to the other side, but in quantum mechanics, there is a small but non-zero probability that the ball will simply appear on the other side of the hill without ever going over it. It tunnels through the hill. This is quantum tunneling, and it is not a theoretical curiosity. It is a well-established phenomenon that is responsible for nuclear fusion in stars, radioactive decay, and the operation of many electronic devices. Vilenkin proposed that the entire universe tunneled into existence in the same way. Before the tunneling event, there was nothing. Not empty space, not a quantum vacuum, not a pre-existing framework. Nothing, no space, no time, no matter, no energy, no laws. Absolute, total, philosophical nothing. And then, with some probability, a tiny, closed quantum universe tunneled into existence and immediately began to inflate. The tunneling event created space, time, matter, energy, and the laws of physics all at once. It was the ultimate free lunch, the creation of everything from nothing. Vilenkin was very specific about what he meant by nothing. He wrote, "The tunneling is from literally nothing. What I mean by nothing is not just the absence of matter. It is the absence of space, time, and everything else, including the laws of physics." And yet, his mathematical framework showed that this process has a non-zero probability. The probability is not large, but it is not zero. And in a context where there is no time, probability does not mean what it usually means. There is no waiting. There is no duration over which events can happen. The tunneling is not an event in time. It is the creation of time itself. This is perhaps the most radical scientific proposal ever made about the origin of the universe. It says that the universe requires no cause, no pre-existing framework, no creator, no antecedent conditions. It just happened. It tunneled into existence from absolute nothing, and the mathematics of quantum cosmology shows that this is possible. Planck has famously said, "Many people suspect that the universe was created out of nothing. This is now supported by science." He has also said, "The probability of the universe being created from nothing is non-zero. And if the probability is non-zero, then given enough, well, not even time, because there is no time, the tunneling will happen, it must happen, nothing is unstable." That last phrase is worth lingering on, nothing is unstable. Think about what this means. We normally think of nothing as the most stable state possible. If there is nothing, what could possibly change? But Planck is arguing the opposite. Nothing is the most unstable state possible. Nothing cannot remain nothing. The laws of quantum mechanics, or perhaps something even deeper than quantum mechanics, ensure that nothing will spontaneously generate something. The void is pregnant with potential. The absence of everything is paradoxically full of possibilities. This connects back to the quantum vacuum we discussed earlier, where the Heisenberg uncertainty principle prevents true emptiness. But Planck goes further. Even without a quantum vacuum, even without the Heisenberg uncertainty principle, even without any pre-existing framework at all, the very concept of nothing is unstable. Something will emerge. The question is not why is there something rather than nothing. The question is, how could there ever be nothing? Nothing is impossible, something is inevitable. Of course, this proposal has been criticized, and the criticisms are serious. The most fundamental criticism is the one we have already encountered. Planck says the universe tunneled from nothing, and the tunneling is described by the laws of quantum mechanics. But if there is truly nothing, there are no laws. Where did the laws of quantum mechanics come from? If nothing exists, how can there be a probability of tunneling? Probability is a mathematical concept, and mathematics is something, not nothing. Even the concept of possibility is something. Even the statement "nothing is unstable" implies that there is a state, nothing, which has a property, instability, and properties are something. It seems that no matter how hard we try, we cannot truly start from nothing. Every attempt to derive something from nothing smuggles in some prior structure, some framework, some set of rules. This is the meta-law problem, and it is one of the deepest and most stubborn problems in the philosophy of physics. Some physicists respond by arguing that the laws of physics are not things that exist. They are descriptions of regularities. They are not prior to the universe. They emerge with the universe. The universe and its laws are a package deal. You cannot have one without the other. In this view, the question, "Where did the laws come from?" is like asking, "Where did the shape of a sphere come from?" The shape of a sphere is not something imposed on the sphere from outside. It is an inherent feature of what it means to be a sphere. Similarly, the laws of physics are not imposed on the universe from outside. They are inherent features of what it means to be a universe. But even this response is not entirely satisfying. Why these laws? Why quantum mechanics? Why general relativity? Why these particular mathematical structures and not others? These questions remain open, and they may remain open forever. Let us now turn to one of the most mind-bending and controversial ideas in all of modern physics: the multiverse. Specifically, the version of the multiverse that arises from eternal inflation. We discussed cosmic inflation earlier, the brief period of exponential expansion that occurred in the very early universe. We presented inflation as a single event. a brief period of rapid expansion that ended when the inflaton field decayed from its false vacuum state. But here is the remarkable thing about inflation. According to many models, inflation does not end everywhere at the same time. In fact, inflation may never end everywhere. It may be eternal. Here is how this works. During inflation, the inflaton field is in a high-energy state, and quantum fluctuations cause the field's energy to vary from place to place. In most regions, the field eventually decays to a low-energy state, ending inflation in that region and creating a hot Big Bang, a pocket universe like ours. But in some regions, the quantum fluctuations push the field to even higher energies, keeping inflation going. And because inflating space expands exponentially, the inflating regions grow much faster than the non-inflating regions shrink. No matter how many pocket universes form, the total volume of inflating space keeps growing. Inflation, once started, never stops. It produces an infinite number of pocket universes, each with its own Big Bang, its own cosmic history, potentially its own physical constants, and even its own laws of physics. This is eternal inflation, and it was first proposed by Alexander Vilenkin in 1983 and later developed extensively by Andrei Linde, who called his version chaotic eternal inflation. In Linde's picture, the universe is like an infinite, ever-expanding foam, with new bubbles constantly forming. Each bubble is a pocket universe. Our universe is one such bubble, and the total multiverse, the collection of all pocket universes, is infinite in extent and eternal in duration. It has always been inflating and will always be inflating. New pocket universes are being born at every moment, an infinite number of them, each one a complete universe with billions of galaxies and trillions of stars. Now, in the context of our central question, what does eternal inflation say about what came before the Big Bang? The answer is startling in its simplicity. Before our Big Bang, there was more inflation. Our Big Bang was not the beginning of everything. It was a local event, the moment when our particular pocket universe nucleated out of the inflating background. Before our Big Bang, the inflating multiverse already existed, and it may have existed forever. There was never nothing. There was always inflation. There was always something. The question of what came before the Big Bang is like asking what is south of New York City. The answer is not nothing. The answer is New Jersey and then the rest of the world. Our Big Bang is not the southern boundary of existence. It is a point on a much larger map, a much larger cosmic landscape that extends far, far beyond what we can see. But wait, if the multiverse is eternal, does it have a beginning? Can inflation have been going on forever into the past? This is a crucial question, and it was addressed in a landmark paper by Arvind Borde, Alan Guth, and Alexander Vilenkin in 2003. The Borde-Guth-Vilenkin theorem proves that any universe or multiverse that has been, on average, expanding throughout its history must have had a beginning. It cannot be past eternal. The expansion itself implies a beginning. This theorem applies to most inflationary models, and it means that even the eternal inflating multiverse had a beginning. It has been inflating forever into the future, but it has not been inflating forever into the past. At some point, inflation began, and the question of what caused it to begin, of what existed before inflation, remains unanswered. Vilenkin himself has interpreted this result as supporting his quantum tunneling proposal. The multiverse began when a tiny universe tunneled into existence from nothing and began to inflate. From that initial quantum tunneling event, the eternal inflation of the multiverse began, and it has been going ever since, producing an infinite number of pocket universes, of which ours is one. But other physicists interpret the Borde-Guth-Vilenkin theorem differently. Some argue that the theorem has loopholes. It assumes that the universe has been expanding on average, but what if there are periods of contraction? What if the universe bounces? What if the expansion is not monotonic? These possibilities, which we will explore shortly, may allow the universe to be truly past eternal, evading the theorem. The debate is ongoing and unresolved. The multiverse raises another profound question. If there are infinitely many pocket universes, each with different physical constants and possibly different laws of physics, then the fact that our universe has the specific constants and laws needed for life is not surprising. It is simply a selection effect. We observe this particular universe because this particular universe supports observers. If the constants were different, there would be no one to observe them. This is the anthropic principle, and it provides a potential explanation for the apparent fine-tuning of the universe. The physical constants of our universe appear to be extraordinarily finely tuned for the existence of complex structures and life. If the strong nuclear force were slightly stronger, hydrogen would not exist, and the primary fuel of stars would be gone. If it were slightly weaker, complex nuclei would not be stable. If the electromagnetic force were slightly different, chemistry as we know it would not work. If the cosmological constant were slightly larger, the universe would have expanded too rapidly for galaxies to form. If it were slightly smaller, or negative, the universe would have collapsed. The list goes on and on. Dozens of physical constants and parameters appear to be set to precisely the values needed for a complex, interesting universe. The probability of this happening by chance is unimaginably small, like winning the cosmic lottery billions of times in a row. The multiverse provides a possible explanation. If there are infinitely many universes with randomly varying constants, then some of them, by pure chance, will have constants compatible with life. And those are the universes where observers exist to marvel at the fine-tuning. It is like a cosmic lottery with an infinite number of tickets. If you buy infinitely many tickets, you are guaranteed to win, no matter how improbable the odds. We are the winners of the cosmic lottery, not because we are special, but because we could not exist in a universe where we did not win. This is a satisfying explanation for some people, and a deeply unsatisfying one for others. Critics argue that the multiverse is untestable, and therefore unscientific. If we can never observe other pocket universes, if we can never confirm their existence, then the multiverse is not a scientific theory, but a philosophical speculation, a metaphysical hypothesis dressed up in mathematical clothing. The physicist Paul Steinhardt, who ironically was one of the early developers of inflationary theory, has become one of its fiercest critics, arguing that eternal inflation and the multiverse make the theory unfalsifiable, and therefore scientifically useless. Others disagree. They argue that the multiverse makes statistical predictions about the properties of our universe, and these predictions can be tested. If the multiverse is real, the properties of our universe should be typical of universes that support observers. If our universe turns out to be atypical, this would count as evidence against the multiverse. This is an active area of research, and the debate about the scientific status of the multiverse is one of the most important ongoing debates in physics and philosophy of science. Now, let us explore one of the most creative and beautiful theories about what came before the Big Bang. This is conformal cyclic cosmology, or CCC, proposed by the legendary mathematical physicist and Nobel laureate Sir Roger Penrose. Penrose, who won the Nobel Prize in Physics in 2020 for his mathematical proof that black holes are a robust prediction of general relativity, has spent decades thinking about the deep structure of the universe, and CCC is his answer to the question of what came before the Big Bang. The basic idea of CCC is that the universe goes through an infinite sequence of cycles, which Penrose calls aeons. Each aeon begins with a Big Bang and ends with an infinitely expanded, infinitely diluted state that Penrose calls the remote future. And here is the extraordinary twist. The remote future of one aeon is identical, in a precise mathematical sense, to the Big Bang of the next eon. The end becomes the beginning. Death becomes birth. The universe is eternal, recycling itself endlessly through an infinite sequence of aeons. To understand how this works, we need to understand a mathematical concept called conformal geometry. In ordinary geometry, size matters. A small circle is different from a large circle. A short line is different from a long line. But in conformal geometry, size is irrelevant. All that matters is angles. A conformal transformation can change the size of everything without changing any angles. A small circle and a large circle are conformally equivalent. A tiny universe and a vast universe are conformally equivalent, as long as their geometries have the same angular relationships. Now, here is Penrose's key insight. At the very beginning of the universe, near the Big Bang, everything is incredibly hot, dense, and concentrated. The universe is tiny. Matter exists mostly as radiation, particles moving at or near the speed of light. Radiation is conformally invariant, meaning it behaves the same way regardless of the overall scale. At the very end of the universe in the remote future, everything is incredibly cold, dilute, and spread out. The universe is vast. All black holes have evaporated through Hawking radiation. All massive particles have decayed. All that remains is radiation, photons, and gravitons spreading through an ever-expanding cosmos. And this final state, like the initial state, is conformally invariant. Both the beginning and the end of the universe are dominated by radiation, and both are conformally invariant. In conformal geometry, the tiny, hot, dense initial state and the vast, cold, dilute final state are identical. They are the same state, viewed at different scales. And so, Penrose argues, the remote future of one aeon naturally transitions into the Big Bang of the next aeon. No special mechanism is needed. No quantum tunneling, no external cause. The geometry of the universe itself ensures that the end flows into the beginning. The universe is a cosmic phoenix, endlessly dying and being reborn. This is a profoundly beautiful idea. It means that the Big Bang was not the absolute beginning. It was a transition. Before our Big Bang, there was a previous aeon, a previous universe that lived, evolved, and eventually died, its matter decaying into pure radiation, its space expanding to infinite extent. And that dying universe, in its final moments, looked exactly like the birth of our universe. And before that aeon, there was another, and before that, another. Infinitely far back, an infinite chain of aeons, each one a complete universe with its own galaxies, stars, planets, perhaps its own forms of life and consciousness. This is the cyclic vision of cosmology, echoing ancient Hindu and Buddhist ideas of eternal cosmic cycles, but now expressed in rigorous mathematical physics. And Penrose claims there is evidence for this. If CCC is correct, then events in the previous aeon should leave traces in our cosmic microwave background. Specifically, the evaporation of supermassive black holes in the previous aeon should produce concentric circles of slightly unusual temperature in the CMB, which Penrose calls Hawking points, named after Stephen Hawking, whose theory of black hole radiation makes them possible. Penrose and his collaborator Vahe Gurzadian have analyzed CMB data and claim to have found evidence for these Hawking points. They claim to have detected anomalous circular patterns in the CMB that are consistent with the predictions of CCC. This is extraordinary. If confirmed, It would be direct observational evidence that a universe existed before our Big Bang. It would be a message from the previous aeon, encoded in the oldest light we can see, telling us that we are not the first and we will not be the last. But the claimed evidence is highly controversial. Many cosmologists have challenged Penrose's analysis, arguing that the circular patterns can be explained by known statistical effects and do not require CCC. The debate is ongoing, and the evidence is far from conclusive. CCC also faces theoretical challenges. It requires that all massive particles eventually decay, including protons. Proton decay is predicted by some grand unified theories, but has never been observed. Current experiments have placed the proton half-life at greater than 10 to the power of 34 years, but CCC requires that protons do eventually decay on some timescale. If protons are truly stable, CCC does not work, because the remote future would contain massive particles, not just radiation, and the conformal transition would not be possible. Additionally, CCC requires a specific mechanism for dealing with the information contained in black holes. When a black hole evaporates, what happens to the information it consumed? This is the black hole information paradox, one of the most important unsolved problems in theoretical physics. Penrose has proposed that information is indeed lost in black holes, contrary to the mainstream view in quantum gravity. This is a minority position, and it makes CCC dependent on a controversial assumption. Despite these challenges, CCC remains one of the most creative and mathematically sophisticated proposals for what existed before the Big Bang. It is a testament to Roger Penrose's genius and his willingness to think differently about the deepest questions in physics. Now, let us journey into the realm of string theory, one of the most ambitious and controversial frameworks in modern theoretical physics. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional vibrating strings of energy. Different vibration patterns of these strings correspond to different particles. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is a string vibrating yet another way. All the particles in the Standard Model, and many more, are different notes played on the same cosmic instrument. String theory requires extra dimensions beyond the 3 spatial dimensions and one time dimension that we experience. The most common version, superstring theory, requires 10 dimensions. M theory, which unifies the 5 different versions of superstring theory, requires 11 dimensions. The extra dimensions are assumed to be compactified, curled up into shapes so tiny that we cannot detect them, at scales near the Planck length. The specific way in which the extra dimensions are compactified determines the physical constants and particle content of the universe we observe. And here is the connection to our central question. String theory gives rise to a specific proposal for what came before the Big Bang, called the ekpyrotic model. Developed by Justin Corey, Bert Overut, Paul Steinhardt, and Neil Turok in 2001, and later extended into the cyclic model by Steinhardt and Turok. The ekpyrotic model is based on the idea of branes, short for membranes. In M theory, our 3-dimensional universe may be a 3-dimensional brane, a membrane-like object floating in a higher dimensional space called the bulk. And our brane may not be alone. There may be other branes nearby in the bulk, parallel to ours, separated by a small distance in an extra dimension that we cannot perceive. The ekpyrotic model proposes that the Big Bang was caused by a collision between 2 branes. Our brane and a neighboring brane were initially separated, drifting through the bulk. At some point, they collided. The collision released enormous energy, heating both branes to incredible temperatures and flooding them with matter and radiation. From the perspective of observers on either brane, this collision looked exactly like a Big Bang. The universe appeared to burst into existence from a hot, dense, uniform state, and then expanded and cooled. But from the higher dimensional perspective, it was just two branes bumping into each other. And in the cyclic version of this model, the branes do not collide just once. They oscillate, moving toward each other, colliding, bouncing apart, and then falling back together again, over and over, in an eternal cycle. Each collision creates a Big Bang. Each period between collisions is a cosmic epoch during which matter and energy cool, structures form, and life can arise. And then the branes collide again, and everything is reset. A new Big Bang, a new cosmic epoch, new galaxies, new stars, new planets, potentially new forms of life. In this picture, there was something before the Big Bang. There was a previous cosmic epoch, a previous period when the branes were separating after a previous collision. And before that, there was another collision, and before that, another period of separation, stretching back infinitely into the past. The universe is eternal, cycling endlessly through an infinite series of Big Bangs, like a cosmic heartbeat. The ekpyrotic and cyclic models have some attractive features. They provide an alternative to inflation, explaining the uniformity and flatness of the universe without requiring a period of exponential expansion. They provide a natural mechanism for the Big Bang, the brane collision, and they make the universe eternal, avoiding the problem of an absolute beginning. But they also face serious challenges. The dynamics of brane collisions are not well understood. It is not clear whether the collision would actually produce the smooth, uniform initial conditions that we observe. Some calculations suggest that the collision would be chaotic and violent, producing a highly inhomogeneous universe, nothing like what we see. Additionally, string theory itself, despite decades of intensive research, remains unproven. There are no experimental confirmations of string theory. No one has observed extra dimensions, no one has detected a string, and the energy scales at which string effects become important are far beyond the reach of any current or foreseeable experiment. The critics of string theory, most notably the physicist Lee Smolin and the mathematician Peter Voigt, have argued that string theory is not even wrong, a phrase attributed to the physicist Wolfgang Pauli, meaning that it makes no testable predictions and therefore does not qualify as a scientific theory. Proponents of string theory counter that the mathematical consistency and elegance of the theory, and its ability to naturally incorporate gravity, make it the most promising candidate for a fundamental theory of nature, even if direct experimental tests are currently out of reach. Now, let us turn to a theory that addresses our central question with a very different approach. Loop quantum cosmology and the Big Bounce. Loop quantum gravity, or LQG, is the main competitor to string theory as a candidate theory of quantum gravity. While the string theory starts from quantum mechanics and tries to incorporate gravity, LQG starts from general relativity and tries to quantize it directly. The central idea of LQG is that space is not continuous but discrete. Space is made up of tiny, finite, indivisible chunks, quantum units of volume and area, connected in a network called a spin foam. The Planck length, approximately 10 to the negative 35 meters, is the smallest meaningful unit of space. You cannot have a distance shorter than the Planck length, just as you cannot have less than one atom of an element. Space is granular, like a mosaic made of unimaginably tiny tiles. And this granularity has profound consequences for the Big Bang singularity. In classical general relativity, as we trace the universe backward in time, the density increases without bound, reaching infinity at the singularity. But in LQG, this cannot happen. The quantization of space creates a maximum density, a limit beyond which matter cannot be compressed. It is like trying to squeeze a liquid into less than zero volume. The atomic nature of matter prevents it. Similarly, the quantum nature of space prevents infinite compression. And what happens when you reach this maximum density? The universe does not end at a singularity. It bounces. The collapsing universe reaches maximum density and then rebounds, expanding outward in a big bang. This is the Big Bounce, and it is one of the most studied predictions of LQG, computer simulations of loop quantum cosmology, performed by Abhay Ashtekar, Tomasz Pawlowski, Parampreet Singh, and others, have shown that when you model a universe collapsing under the equations of LQG, the singularity is replaced by a bounce. The universe passes smoothly through maximum density and emerges expanding. From the perspective of observers on the other side of the bounce, it looks exactly like a Big Bang. But it is not a beginning. It is a transition from a previous contracting phase to the current expanding phase. What was before the Big Bang? According to the Big Bounce, there was a previous universe, a universe that was contracting. That universe collapsed, reached maximum density, and bounced, creating what we call the Big Bang. And before that contracting universe, there may have been an expanding phase, which itself began with a previous bounce. And before that, another contracting phase, and another bounce, and so on, potentially infinitely far into the past. The universe is a cosmic yo-yo, endlessly bouncing between expansion and contraction, with each bounce creating a new Big Bang and a new cosmic epoch. This is a cyclical cosmology, similar in spirit to Penrose's CCC and the ekpyrotic model, but based on very different physics. In the Big Bounce, the cycles are driven by the quantum nature of space, not by conformal geometry or brane collisions. And the Big Bounce makes specific testable predictions. The quantum effects near the bounce should leave subtle imprints in the cosmic microwave background, slight modifications to the spectrum of fluctuations that differ from the predictions of standard inflationary cosmology. Current observations are not precise enough to distinguish between these predictions, but future experiments like the CMB-S4 project and the Lightbird satellite may be able to tell the difference. The Big Bounce has a beautiful simplicity to it. It does not require exotic extra dimensions or parallel branes. It does not require the universe to come from nothing. It does not require imaginary time or conformal geometry. It simply requires that space is quantized, which is a natural and well-motivated consequence of combining quantum mechanics with general relativity. And the result is a universe that has always existed, bouncing endlessly, never beginning and never ending. The singularity, the point of infinite density, the barrier beyond which physics breaks down, is replaced by a smooth, finite transition. The dragon at the edge of the map is tamed by quantum gravity, but the Big Bounce faces challenges too. Loop quantum gravity is not a complete theory. Many aspects of it are still under development. The relationship between LQG and the standard model of particle physics is not fully understood. It is not clear whether LQG can reproduce all the successes of standard quantum field theory, and the specific predictions of the Big Bounce for the CMB are model-dependent, meaning they change depending on the detailed assumptions you make about the pre-bounce universe. The Big Bounce is a promising and active area of research, but it is not yet confirmed. There is yet another fascinating approach to the question of what existed before the Big Bang, and it comes from a completely different direction. It comes from the theory of information and the philosophy of mathematics. The central figure here is the physicist Max Tegmark, who has proposed what he calls the mathematical universe hypothesis. Tegmark's idea is radical, elegant, and deeply strange. He proposes that the physical universe is not just described by mathematics. It is mathematics. The universe is a mathematical structure, not a physical thing that happens to obey mathematical laws, but a purely mathematical object. Particles, forces, space-time, energy, consciousness, you, me, everything. We are all patterns within a mathematical structure. There is no physical stuff underlying the mathematics. The mathematics is all there is. This sounds crazy, and Tegmark himself acknowledges that it sounds crazy. But he argues that it is the logical endpoint of a progression that physics has been following for centuries. In the early days of physics, we described the universe in terms of familiar, tangible things: balls, springs, fluids, waves. But as physics progressed, the tangible things were replaced by increasingly abstract mathematical structures. An electron is not a little ball, it is an excitation of a quantum field. A quantum field is not a substance flowing through space. It is an operator-valued distribution on a manifold. The deeper we go, the more physics becomes pure mathematics. The physical stuff dissolves, and what remains is structure, pattern, relationship, mathematics. Tegmark takes this to its logical conclusion. If physics is mathematics, then the physical universe is a mathematical structure. And if the physical universe is a mathematical structure, then the question of what came before the Big Bang takes on a completely different character. Mathematical structures do not exist in time. They do not have beginnings or endings. They do not come into existence or go out of existence. The number 7 does not have a birthday. The theorem that the square root of 2 is irrational was not created at some point in time. It has always been true and always will be true. It is a timeless, eternal feature of the mathematical landscape. Similarly, if the universe is a mathematical structure, it does not have a beginning. The Big Bang is not the moment when the structure was created. It is a feature of the structure, like the tip of a cone or the cusp of a curve. It is a place where certain variables take extreme values, but it is not an edge or a boundary of the structure itself. The structure exists timelessly, and what we experience as the passage of time is simply our movement through the structure, our exploration of its features. This connects to an even more radical idea. Tegmark also proposes the mathematical universe hypothesis at its most extreme level, which he calls the level 4 multiverse. He argues that not just our mathematical structure exists, but all mathematical structures exist. Every consistent mathematical structure corresponds to a physical universe. There are universes based on different geometries, different number systems, different algebraic structures, different everything. Our universe is one mathematical structure among infinitely many, and the totality of all mathematical structures, the level 4 multiverse, is the ultimate reality. It requires no creation. It requires no explanation. It simply is, in the same way that mathematical truths simply are. Why does 2 plus 2 equal 4? It just does. There is no cause. There is no mechanism. It is a necessary truth. Similarly, the existence of all mathematical structures and the physical universes they correspond to is a necessary truth. There is no need for creation, no need for a creator, no need for a beginning. The question, what came before the Big Bang, dissolves, because the framework in which the question makes sense, the framework of time and causation, is itself part of the mathematical structure rather than something prior to it. This is related to a much older idea that connects to the problem of nothing, the mathematical concept of the empty set. In set theory, the foundation of all mathematics, you start with nothing, the empty set, the set that contains no elements, and from the empty set, using only the rules of set theory, you can construct all of mathematics. The empty set has no elements, but it has one subset itself. So you can form the set whose only element is the empty set. And from those two sets, You can form more sets, and more, building up the natural numbers, the integers, the rationals, the reals, the complex numbers, functions, spaces, structures, all of mathematics, starting from literally nothing. This is the von Neumann construction, and it shows that in a very precise mathematical sense, everything comes from nothing. The entire edifice of mathematics, including the mathematical structures that Tegmark identifies with physical universes, can be derived from the empty set. From nothing. Nothing contains the seed of everything. The void is full of potential. And this is not a metaphor. It is a precise mathematical fact. Now, I want to be honest with you. The mathematical universe hypothesis is extremely speculative. It is not widely accepted by physicists, and many consider it more philosophy than science. It is very difficult, perhaps impossible, to test. How would you determine whether the universe is really a mathematical structure versus a physical thing described by mathematics? The distinction may not be empirically meaningful, but as a framework for thinking about the problem of nothing, it is profoundly suggestive. It suggests that the distinction between something and nothing may be less sharp than we think. It suggests that nothing, properly understood, already contains everything. It suggests that the question, why is there something rather than nothing, may have a mathematical answer, because nothing, in the mathematical sense, is equivalent to everything. We have now explored 7 major theories about what existed before the Big Bang. The Hartley-Hawking no-boundary proposal, which says that time gradually merges with space, and the question of before becomes meaningless. Vilenkin's quantum tunneling from nothing, which says the universe popped into existence from absolute nothingness with a calculable probability. Eternal inflation and the multiverse, which says that our Big Bang was a local event in a much larger, eternally inflating cosmos. Penrose's conformal cyclic cosmology, which says that the universe endlessly cycles through aeons, with the end of one becoming the beginning of the next. String theory and the ekpyrotic model, which says that the Big Bang was a collision between higher dimensional brains. Loop quantum cosmology and the Big Bounce, which says that the Big Bang was a bounce from a previous contracting universe. And the mathematical universe hypothesis, which says that the universe is a timeless mathematical structure, and the Big Bang is a feature of the structure rather than its beginning. Each of these theories is brilliant. Each is based on deep mathematics and profound physical insight. Each has strengths and weaknesses, and none of them is proven. We do not know which, if any, is correct. We are at the frontier of human knowledge, and the landscape ahead is uncharted. But the very existence of these theories, the fact that human beings, living on a small planet orbiting an average star in an unremarkable galaxy, can even formulate these ideas, is one of the most extraordinary things about our species. We are tiny, fragile, short-lived creatures, and yet our minds can reach back to the first fraction of a second of the universe's existence and ask what came before. I want to stop here for just a moment and ask you a question. We have been on this journey together for a while now. Which of these 7 theories resonates with you the most? Which one feels the most right? Or which one blows your mind the most? I want you to comment below. Just put the number 1 through 7 and tell me which theory you find most compelling and why. I am genuinely curious because one of the most fascinating things about these theories is how different people respond to them differently. Some people are drawn to the elegance of the no-boundary proposal. Some people love the radical simplicity of the universe from nothing. Some people are excited by the multiverse. Some people find Penrose's cyclic cosmology the most beautiful. Your response says something deep about how you think about reality, about what you consider good explanation, about what satisfies your curiosity. So share it. And while you are at it, if you're finding this journey as fascinating as I am, subscribe to the channel. We go deep here. We explore the biggest questions with the rigor and curiosity they deserve. And there is so much more to come. Now, let us delve into the deeper problems and unsolved mysteries that underlie all of these theories. Because even the most brilliant theory is only as good as the foundations it rests on. And the foundations of our understanding of the universe have some serious cracks. The first and perhaps most troubling unsolved problem is the cosmological constant problem. The cosmological constant, denoted by the Greek letter lambda, is a term in Einstein's equations of general relativity that represents the energy density of empty space, the energy of the vacuum. Quantum field theory predicts that the vacuum should have an enormous energy density, due to all the virtual particles we discussed earlier. When you add up the zero-point energies of all the quantum fields in the Standard Model, you get a vacuum energy density of approximately 10 to the power of 113 joules per cubic meter. This is an absurdly large number. But when we measure the actual vacuum energy density of the universe by observing the accelerating expansion of the cosmos, we get a value of approximately 10 to the power of negative 10 joules per cubic meter. The theoretical prediction is larger than the observed value by a factor of approximately 10 to the power of 120. That is a 1 followed by 120 zeros. This is the largest discrepancy between theory and observation in the entire history of science. It is not even close. Nothing else comes close. The cosmological constant problem is sometimes called the worst prediction in the history of physics, and it is a deep embarrassment for theoretical physics. What does this have to do with our question about nothing? Everything. The cosmological constant problem is fundamentally a problem about the nature of nothing. It says that we do not understand what empty space is. We do not understand what the vacuum is. We do not understand nothing. Our best theories of the very small quantum field theory and our best theory of the very large general relativity give wildly incompatible answers about the energy of empty space. Something is profoundly wrong with our understanding, and until we fix it, we cannot claim to understand what nothing is, and we certainly cannot claim to understand how the universe arose from nothing. Some physicists believe that the solution to the cosmological constant problem will require a completely new understanding of quantum mechanics, or of space-time, or of both. It may require the theory of quantum gravity that we have been discussing. And when we find that theory, when we understand why the vacuum energy is what it is, we may also understand what came before the Big Bang. The two problems may be deeply connected. The second major unsolved mystery is the arrow of time. Why does time have a direction? Why does it flow from the past to the future rather than the future to the past? At the fundamental level, the laws of physics are almost perfectly time-symmetric. If you film a fundamental physical process and play the film backward, the reversed process also obeys the laws of physics. An electron scattering off a photon looks the same forward and backward. The orbit of a planet looks the same forward and backward. The fundamental equations do not distinguish between past and future. And yet, in our everyday experience, time has a very clear direction. Eggs break, but do not unbreak. Ice cream melts, but does not unmelt. We remember the past, but not the future. We age, we decay, we die. Time flows relentlessly in one direction. From order to disorder, from low entropy to high entropy. This is the second law of thermodynamics, and it is one of the most fundamental principles in all of physics. But the second law is not a fundamental law, it is a statistical law. It says that entropy, a measure of disorder, tends to increase because there are many more disordered states than ordered states. If you shuffle a deck of cards, it is overwhelmingly likely to become more disordered. not because there is a law of nature forcing disorder, but because there are so many more disordered arrangements than ordered ones. And here is the crucial point. The second law explains why entropy increases, but it does not explain why entropy was low in the first place. The arrow of time points from low entropy to high entropy, but why was entropy low at the beginning? Why did the Big Bang produce a state of extraordinarily low entropy? This is the past hypothesis, and it is one of the most puzzling aspects of the Big Bang. Roger Penrose has calculated that the probability of the universe beginning in the specific low entropy state that it did is 1 in 10 to the power of 10 to the power of 123. Let me be clear about what this number means. It is not 10 to the power of 123. It is 10 to the power of 10 to the power of 123. This is a number so inconceivably large that it makes all other large numbers in physics look like zero by comparison. The number of atoms in the observable universe, approximately 10 to the power of 80, is laughably small in comparison. The number of possible chess games, the number of possible histories of the universe, the number of anything you can think of, is trivially small compared to 10 to the power of 10 to the power of 123. And the probability that the universe began in its observed low entropy state by pure chance is 1 divided by this number. It is essentially impossible. And yet, here we are. This means that whatever happened at or before the Big Bang, it must have involved a mechanism that produced a state of extraordinarily low entropy. This is not a minor detail. This is a fundamental constraint on any theory of the origin of the universe. Whatever came before the Big Bang must explain why the universe began in such a special, improbable state. Most of the theories we have discussed do not fully address this. Inflation helps because it can produce a large, smooth, uniform universe from a tiny patch, but it does not fully explain why the pre-inflationary state was low entropy. The big bounce may help if there is a mechanism for entropy to be reset or reduced during the bounce. Penrose's CCC is specifically designed to address this, because the conformal transition between aeons may naturally produce a low entropy initial state. But the problem is far from solved. The arrow of time, the low entropy of the Big Bang, and the deep mystery of why the universe is ordered at all, these remain among the most profound, unsolved problems in physics. The third major mystery is the one I have been circling around throughout this video. The problem of the laws of physics themselves. Where do the laws come from? Why are they what they are? Are they eternal and unchanging, or could they have been different? Do they exist independently of the universe, or are they part of the universe? These questions are not just philosophical curiosities. They are deeply connected to the question of what existed before the Big Bang. If the laws of physics existed before the universe, then something existed before the Big Bang, namely the laws. And we would need to explain where the laws came from, pushing the question back another step. If the laws came into existence with the universe, then we need to explain how a lawless nothing could produce a lawful something. And if the laws are not things that exist at all, but are simply descriptions of the universe's behavior, then we need to explain why the universe behaves in a law-like manner. The physicist John Archibald Wheeler, one of the most creative and visionary physicists of the 20th century, proposed an idea he called law without law. Wheeler suggested that the laws of physics are not eternal, pre-existing rules. They emerged from a deeper, more fundamental level of reality that has no laws at all. At the deepest level, Wheeler believed, there is only chaos, randomness, information, bits. And from this chaotic substrate, through a process that Wheeler compared to natural selection, the laws of physics emerged and stabilized. Wheeler encapsulated this vision in his famous phrase, it from bit. The universe, he argued, is fundamentally made of information, of binary choices, of yes or no questions. And the physical universe, the it, emerges from this informational substrate, the bits. Wheeler illustrated this with his participatory anthropic principle, the idea that observers, conscious beings who ask questions about the universe, play a fundamental role in bringing the universe into existence. This is not the naive idea that consciousness creates reality. It is a subtler idea, inspired by the measurement problem in quantum mechanics, which says that the act of observation is not a passive registration of pre-existing facts, but an active participation in the creation of physical reality. Wheeler suggested that the universe is a self-excited circuit, a loop in which observers bring the universe into existence, and the universe brings observers into existence. The two are inextricably linked. Neither can exist without the other. Wheeler's ideas are visionary but vague. They point in a direction rather than providing a detailed map. But they have inspired a great deal of work in quantum information theory, quantum computing, and the foundations of quantum mechanics. The idea that information is fundamental, that the universe is made of information rather than matter or energy, has gained significant traction in recent years. Leonard Susskind and Gerard de Hooft developed the holographic principle, which says that all the information contained in a three-dimensional region of space can be encoded on its two-dimensional boundary. Juan Maldacena's ADS/CFT correspondence, one of the most important results in theoretical physics in the last 30 years, provides a concrete realization of this principle, showing that a theory of quantum gravity in a certain type of spacetime is mathematically equivalent to a theory without gravity living on the boundary of that spacetime. These results suggest that spacetime itself, the arena we thought was fundamental, may be emergent, may arise from a deeper, non-spatial, purely informational structure. And if spacetime is emergent, then the Big Bang, which is an event in spacetime, is also emergent. It is not a fundamental event but a derived event, emerging from something more primitive. The question of what came before the Big Bang may be the wrong question, not because there is no answer, but because the question assumes that spacetime, and therefore time, and therefore before, are fundamental. If they are not, then the question needs to be reformulated in terms of the more fundamental structure from which spacetime emerges, and we do not yet know what that structure is. This connects to one of the most active areas of research in modern theoretical physics, the emergence of spacetime from quantum entanglement. In 2010, the physicist Mark van Ramsdonk published a provocative paper titled "Building Up Spacetime with Quantum Entanglement." Van Ramsdonk argued that the connectedness of spacetime, the fact that nearby regions of space are connected to each other, and that you can travel smoothly from one point to another, is a consequence of quantum entanglement between the quantum fields in those regions. If you remove the entanglement, the spacetime becomes disconnected. It breaks apart into separate, unrelated fragments. Entanglement is the glue that holds spacetime together. This idea has been developed further by many researchers, and it suggests a remarkable picture. Spacetime is not fundamental. It is woven from quantum entanglement. Space is not a pre-existing stage on which things happen. It is a consequence of the relationships between quantum systems. And if spacetime is emergent, then the Big Bang singularity, which is a breakdown of spacetime, may not be a physical event at all. It may be an artifact of our description, a place where our proximate emergent notion of spacetime breaks down, and we need to look at the underlying quantum structure. In this picture, asking what came before the Big Bang is like asking what is north of the North Pole, but for a different reason. Not because time does not extend beyond the Big Bang, but because time itself is an emergent approximation that loses meaning at the Big Bang. The underlying quantum structure may not have a before in any meaningful sense. Let me now turn to another deep and fascinating topic that is directly relevant to our question: the concept of the wave function of the universe and the many worlds interpretation of quantum mechanics. In quantum mechanics, a system is described by a wave function, a mathematical object that encodes the probabilities of all possible measurement outcomes. When you measure a quantum system, the wave function appears to collapse, to jump from a superposition of many possibilities to a single, definite result. This is the measurement problem, and it is the most fundamental interpretive puzzle in quantum mechanics. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a radical solution. It says that the wave function never collapses. Instead, every time a quantum measurement is made, the universe splits into multiple branches, one for each possible outcome. All outcomes happen, but in different branches of a vast, ever-branching multiverse. In one branch, the electron went left. In another branch, the electron went right. Both branches are equally real, but they can no longer interact with each other. They have decoherent, become separate, disconnected branches of the universal wave function. If the many worlds interpretation is correct, it has profound implications for the question of what came before the Big Bang. The wave function of the universe, the universal quantum state, may be eternal and all-encompassing. It does not have a beginning or an end. The Big Bang is not the beginning of the wave function. It is a feature within one branch, or many branches, of the wave function. Other branches may have different histories, different Big Bangs, different physical constants, different everything. The universal wave function simply is, timelessly containing all possible histories of all possible universes. In this picture, asking what came before the Big Bang is like asking what is in the other chapters of a book when you are reading chapter 5. The other chapters exist. They are part of the same book, but they are not before or after chapter 5 in any fundamental sense. They are different parts of the same structure. The many worlds interpretation is controversial. Many physicists reject it because it seems extravagant, postulating an enormous number of unobservable parallel universes to solve the measurement problem. Others embrace it because it is the simplest interpretation, requiring no additional postulates beyond the basic equations of quantum mechanics. The equations say that all outcomes happen, and the many worlds interpretation takes the equations at face value. The debate continues, and it may never be resolved to everyone's satisfaction. But the many worlds interpretation reminds us that quantum mechanics, properly understood, may be far stranger than we think, and that the question of what came before the Big Bang may need to be phrased very differently in a truly quantum universe. Now, I want to discuss what some of the greatest minds in the history of physics have said about our central question, because their words illuminate not only the science, but also the emotional and philosophical dimensions of the question. Albert Einstein, the greatest physicist since Newton and arguably the greatest physicist of all time, initially believed that the universe was static and eternal. When he developed his general theory of relativity in 1915, his equations predicted that the universe should be either expanding or contracting. This troubled Einstein deeply. He believed in a steady, unchanging cosmos, and so he added a term to his equations, the cosmological constant, specifically to counteract the expansion and make the universe static. When Edwin Hubble discovered in 1929 that galaxies are moving away from us and that the universe is expanding, Einstein realized his mistake. He reportedly called the cosmological constant his biggest blunder. The universe was not static, it was expanding, and if it was expanding, then in the past it was smaller, denser, hotter. Run the clock backward far enough, and the universe was a point of infinite density, a singularity, a beginning. Einstein was uncomfortable with this. He wanted the universe to be eternal, to have no beginning and no end, but his own equations predicted otherwise. In a letter to a friend, Einstein wrote, "I want to know how God created this world. I am not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are details." This was not a statement of religious belief. Einstein's God was not a personal deity. It was a metaphor for the deep order and rationality of the universe. Einstein wanted to understand the fundamental principles, the deep structure, the ultimate reason why the universe is the way it is. And the question of what came before the Big Bang, of why there is something rather than nothing, was at the heart of this desire. Stephen Hawking spent more time thinking about this question than perhaps any other physicist in history. His views evolved significantly over the decades. In his early work with Roger Penrose in the late 1960s, Hawking proved that the Big Bang singularity was unavoidable in general relativity. If the universe obeys general relativity and contains enough matter and energy, there must have been a singularity. This was a mathematical theorem, not a speculation. It was proof that general relativity predicts its own breakdown at the beginning of the universe. But Hawking then spent the next several decades trying to go beyond this result, trying to understand what quantum effects would do to the singularity. The no-boundary proposal, which we discussed earlier, was his most famous contribution to this effort. It eliminated the singularity by replacing it with a smooth, rounded geometry in imaginary time. The universe simply is, without a boundary or a beginning. In his popular book, A Brief History of Time, Hawking wrote, "So long as the universe had a beginning, we could suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place, then, for a creator?" This was Hawking at his most provocative, using physics to address one of the oldest questions in theology. And in his later book, The Grand Design, co-written with Leonard Mlodinow, Hawking went further. Because there is a law such as gravity, the universe can and will create itself from nothing. Spontaneous creation is the reason there is something rather than nothing, why the universe exists, why we exist. It is not necessary to invoke God to light the blue touch paper and set the universe going. This statement generated enormous controversy, both among scientists and the general public. Many critics pointed out that Hawking had not actually explained why there is a law such as gravity, or why the universe obeys quantum mechanics, or why anything at all exists. He had shown that, given the laws of physics, the universe can arise spontaneously. But the existence of the laws themselves was left unexplained. Hawking, characteristically, was not troubled by this objection. He believed that the laws of physics were not imposed from outside the universe but were part of the universe itself, and that asking where they came from was like asking what is north of the North Pole. The question dissolves when you understand the geometry.